Hello and welcome back, astronomy enthusiasts. This is the lecture that would have been given on Thursday, April 9th. And it is a very exciting day. It's Black Hole Day. We get to talk about black holes. So let's waste zero time and get right into today's review question, which is, wait for it. How do we know that pulsars must be neutron stars? Is it that only objects that dense could physically pulsate that fast? Is it that only objects that small could spin that fast? Is that only objects that are supported by neutron degeneracy pressure could have polar jets? What do you think? You can pause and answer if you'd like. Let's go through them one at a time. It can't be C. We know that there are things other than neutron stars that have bipolar jets, like baby stars that are just normal stars and are nothing degenerate at all about them. So it's not C. It's also not A, because pulsars aren't physically pulsating. They are not physically getting larger and smaller, even though they're called pulsars. I know. In fact, they're rapidly spinning neutron stars, and in fact, it is B. Only objects that are that small could spin that fast. Great. Okay, so let's get to it. Without further ado. Oh, well, this got all messed up, didn't it? That's odd. Anyway, this should say chapter 24, black holes and curved space-time. So let's get to it. Black holes. Before we get to black holes themselves, we need to do a little bit of background reading or an understanding of what's actually going on. And we need to go back to this guy. You may have heard of him. His name is Albert Einstein. We've already seen his name come up in the context of energy and mass equivalence when we were figuring out how the sun generated energy, and he comes back in a major way in this particular class. So gravity, right? Einstein unlocks the why of gravity. You may think that that's unusual, but let's go back and think about where we were with gravity before 1916. You go back to Newton. Newton laid down the law of gravity. If you look at the equation that we wrote down at the beginning of the class for gravity, let me go ahead and do that, and we can remind ourselves what we're talking about. It was this equation: force of gravity is equal to G times the mass of one object, the mass of the other object, divided by their distance squared. Just to remind you, we're talking about the gravitational force felt between two different objects of M1 and M2, separated by a distance D, or R. Sorry, I called it R. Right? That's what we're talking about. Isaac Newton in the 1600s wrote this equation down and understood it as the universal law of gravitation. And it was a major breakthrough in the 1600s. It explains how and why apples fall off of trees. It explains why the moon goes around the earth. It explains why the earth goes around the sun. But even, it doesn't explain why, right? Why is it that two objects separated by some space should feel a force? What is it about these objects that causes a force on the other one? It kind of weirded Newton out, to be honest. And since it's been called spooky action at a distance, right? These two objects in space that are not physically connected in any way are somehow exerting forces on one another. How? Why? Newton didn't know. And it wasn't until 1916, when Einstein came along, that we actually began to figure some of this stuff out. So let's go back to our slideshow. Here we go. Great. Einstein unlocks the why. So what is the why? Let's begin the answer. Well, we'll talk about in a second. One of Einstein's major discoveries in the development of his general theory of relativity, which is his theory of gravity, is the principle of equivalence. Let's talk briefly about the principle of equivalence. We've already seen our dude in an elevator, right? Here's our dude in an elevator. Remember, when the elevator isn't moving or when it's moving upward or downward at constant rate, dude has his normal weight measured on the scale. If that elevator accelerates downwards, he will seem lighter than normal. If that elevator accelerates upwards, he will be heavier than normal, meaning the scale will actually read a higher number as it accelerates upwards. Not just moving up or down, but accelerating up or down. That's important. That's what these arrows mean. And remember, if we cut the cord altogether and let this elevator drop to the floor, dude inside and everything in it is weightless, is exerting zero force on the scale, because dude and elevator and everything in it are falling at exactly the same weight. There's no, it's at the same rate. And so dude is exerting no weight on the scale at all. The principle of equivalence says this: dude locked in this elevator, so let's say, talk about this weightless person here, right? So there's two possibilities for this weightless person. Either dude is in the elevator and falling towards the ground, or dude is in a completely empty universe with no other masses around, and therefore there's no force of gravity pulling dude down to exert a force on the scale. The equivalence principle says that there is no experiment that this person can do trapped inside this elevator that can distinguish between those two things. There is no experiment that will tell them the difference between free falling towards an object that has a lot of mass and being weightless in space with no massive object even around it. That's the principle of equivalence. And everything that follows sort of comes from that first beginning point. Let's take a quick look at this. Two people jump down an infinite hole and play catch with each other, right? Person one and person two, obviously from the ground, as we're observing them, they are accelerating downwards. The further they fall, the faster they fall. And if there's no air resistance, they're going to all fall at the same rate. But from the people's perspective, they're all falling at exactly the same rate. And if you were to take their perspective, let's say they brought a ball with them, they are weightless. Person one is weightless. Person two is weightless. The ball that they bring with them is weightless. They could play catch with this ball. What would that look like? Well, for somebody watching from the outside, the ball is accelerating downward to the same as everything else. But the perspective of these two people, that ball, if they can't see anything falling around them, is simply moving back and forth in a straight line between them, with no other apparent forces acting on it at all. This is very similar to weightlessness as observed in the International Space Station. Two people in the International Space Station, here they are, person one and person two, can play catch in exactly the same way with a ball. Just simply move it back and forth. It will move in a straight line, seemingly from their perspective, and no outside forces seem to be acting on it at all. In fact, we know that these two people and the ball and the orange and the space station and everything else with them are in fact in free fall. It's orbiting the Earth. It is constantly accelerating. But inside, they can't tell. And not only that, there's no experiment that they can do that will actually tell them. Okay, so that's all well and good. That doesn't even really tell us much yet, though. But there's one interesting thing that this principle tells us that happens differently than Newton envisioned it. So let's think about this thought experiment that someone could do. Here is a space shuttle. I realize this is old. The space shuttle hasn't flown in a decade. But here it is, a space shuttle orbiting the Earth. Okay, we're going to do a light experiment now, right? So we're going to shine a laser from the back of this space station and see what path it takes, right? We know what this space station is actually doing. This space shuttle is actually doing. It's orbiting the Earth. So by the time it goes from the back of the ship to the front of the ship, the actual space station has accelerated. It has turned a little bit in the downward direction towards the Earth. Now, if this person was wanting to do an experiment and light was not affected by gravity, the person would be able to do an experiment that would be able to tell whether they were in orbit around the Earth or whether they were flying in a straight line. Let me tell you, let me go back to our camera for a moment, and let's think about this. According to Newton, the force of gravity is directly proportional to the mass of the one object times the mass of the other object. In the case of a light particle orbiting the Earth, what are those two masses? Mass 1 is the mass of the Earth. Mass 2 is the mass of the light particle. Do you remember what the mass of a light particle is? Maybe we'd even talk about it because it wasn't important when we talked about light. But let me tell you now. A light particle has 0 mass. So it doesn't matter how massive your object 1 is. If your object 2 is 0, anything times 0 is 0, and you expect, Newton would say, that light particles do not experience gravity at all because they are massless, and therefore nothing acts on them gravitationally. But Einstein proves that this cannot be the case. Einstein proves that if the principle of equivalence is right, it cannot be that light is unaffected by gravity. Let's go back to PowerPoint. Because if light were unaffected by gravity, then you could do an experiment to tell whether you were in a space station orbiting the Earth or whether you were not. And this is the experiment. A photon unaffected, a light particle unaffected by gravity, will appear to curve if gravity and the space station is actually affecting the space shuttle as it goes. If you take the perspective of a person who is here, right, was here when it started and is here now at some other time, in the time that it's taken that light to move from here to here, it will have seemed to have taken a path that will have curved it to the outside of the bay. And so therefore, it must be the case, since this can't happen, you can't have an experiment that does that, it must be the case that light, in fact, does follow gravity. Gravity does affect light and its travel. So gravity, according to Newton, G equals m1, m2 over r squared, does not affect light. According to Einstein, light is affected by gravity. So why is that? Why is it? What is it about space-time that causes light to bend? What is it about space-time? I've coined this term. I've used this term. I haven't even talked about what it is yet. What is it about masses that cause other masses and light to be deflected and attracted to them? That will be the topic of our next video. So stay tuned.